Hi, Fractally friends. Happy Sunday. I want to share something quickly. I was going to just type, and I probably still will, but I thought it would be quicker to show you. So high level, we are working on finishing up the dispatch experiments. And to do that, we have an entire process to go from discovering stuff in a container through actually generating the job spec, submitting to a scheduler that has Fluxion, also accounts for subsystems, making a match, transforming a job spec, dispatching it, and then running it. And the insight that I had yesterday is that the job spec that initially gets submit to Fluxion cannot be the same as the job spec that eventually runs on the cluster. Why is that? Well, this initial job spec needs to be very general. It needs to say, I need this size of resources, and I know I want to run lamps with this data, but I don't know the cluster that I'm hitting. So I can say that I need 4 nodes or maybe 5 nodes. You can put an or statement. And I need this kind of network fabric, but I can't put, for example, the number of cores. I don't know. And so the strategy we're taking with FluxQ is to have an agent create an initial job spec that is general. This general job spec can then match against many different clusters, and it's not going to be filtered out because it's not, overfitting essentially. Now, once we get to a cluster, that's where when I first did it, trying to use one job spec, I got a lot of errors because you have to get the command exactly right, but how can you get it right if you don't know where it's going? The answer is that we need an agent that's running under the allocation that receives it and says, okay, this was the initial general command that the user wanted. Now, how do I tweak this so it works really well for this cluster, which I have a total view of? This also goes with the philosophy that we figured out when we're working on quantum resources, that you want your agents generally not running, or actually, this is more my opinion. I don't like designs that have agents running at system level components because that requires putting a credential in a system tool. And I think that's absolutely a bad idea. My preference is to put the credentials in the user space. So before you submit the job, maybe it gets passed something to the job. And so in this case, we're using a Kubernetes secret, which again is owned by me, the user. So what I'm going to show you is a new agent we have called the Flux Secretary, which basically wraps a Flux command. And actually, you can see it here in this mini cluster. And the Flux Secretary is going to be launched under this allocation. It's going to use a particular model. We're going to tell it 3 nodes, but actually this cluster only has 2. And then you tell it I want to run OSU all reduce. It is going to figure out the best way to do that. So let's actually get this running, and then I will probably keep talking because that's kind of what I do. So this is actually a case that I set up. I wanted it to fail. I gave it the wrong size, so I'm only actually giving it 2 nodes, but I'm asking for 3. I'm also running this on a Google Cloud cluster that has no fabrics. It just has Ethernet, and I'm giving it a lib fabric container. So I could tell you right away, this needs all these omp MPI variables that it does not have. It's going to fail, but we're going to watch the secretary figure that out. So let's do logs, OSU, all reduce 0. 0 is the lead broker. So here we're installing it. This part is this pre-command here. This is just a janky way to find the Flux version, the Python version installed in the container, and then we're installing it for pip. That could be installed in your Flux view, so you don't have to do it at the runtime. But honestly, when you're using an agent, the install time here is fairly trivial. I mean, all in all, I'm sure we'll have to eventually account for it. So we install the Flux Secretary. This is on GitHub. This has a backend for AWS Bedrock, which is what I'm using now. It also has a backend for my friend Claude, the Claude SDK in Blue Cloud. Okay, so we started running here. So the agent says, I will start by checking what resources this allocation actually has. Good idea, agent. It only has 2 nodes, not 3. A 3-node request would be rejected outright. Let me launch across both your nodes. So it immediately found my first trick. I was not very clever, but so now it is adding, let's see, exclusive. Very nice. So it added affinity. Doesn't need GPU affinity, but with Flux, that doesn't really matter. It also asked for exclusive. It figured out the right number of tasks and cores per task. This is going to give us an error. I can tell you that because this container is old. It is from 2024, and this also is expected to be run on AWS with LaFabric. So let's watch. Let's have MPI throw up on us. There it is. That beautiful throw up that if you ran the performance, any of our performance study runs, you probably are used to. So let's see what the agent says. The agent is getting this error. The launch layout is fine. This is a fabric problem. That's correct. Oh, it apparently already fixed it. The launch succeeded. Here's what happened. The task was you asked for 3. Okay, so there's the task issue. Valid commute, the printed header started. Oh, that's too fast. I couldn't read it. Okay, so let's look here. Fix. I bypassed OFI entirely, changing these environment variables. So this is the fix that the human would have to do. This would have taken me more than 2.5 seconds to do. I would have had to delete the mini cluster, recreate it, probably shell in. And this is also an interesting point because a lot of times we're like, oh, running an agent is going to take all this time. It's going to be more costly. But you just saw how quickly that happened, right? It fixed it really quickly when it got the output. So I don't know, I think the idea of giving the agent this very scoped, controlled environment and letting it fix it while it's in the allocation is actually very advantageous and in that it might actually save money. And anyway, then it spits out all of the final results. So what we're doing for our final dispatch experiments, the big turkey kahuna study, we are using all of our performance study containers that I don't know what's in them and I don't want to know. We have a discovery agent that goes inside, looks around, figures out what's in there, writes a manifest that says exactly what's in there. That manifest is given to an agent that it writes a job spec for Fluxion. It is a general job spec that asks for a number of nodes and then the subsystems that it needs. That job spec is then submit to our Flux queue, which has Fluxion running with custom code that I wrote that basically will satisfy across subsystems like network, etc. And then it will match for containment. It finds the cluster. It still does the transform because we have to take like a job spec and turn it into, for example, a Kubernetes Flux mini cluster. That is deterministic because it's relatively straightforward and I don't want to put an agent in the scheduler. Then it gets dispatched. So that's also part of Flux queue. Once it gets dispatched, we have this guy, the Flux Secretary. He's on GitHub. I can send the link. Run the job and finish, and then we'll get a result. And so what we're doing for the experiments is we're running these experiments with descriptive metadata, so with all the subsystems, and then without. And if the descriptive metadata has value, which I hope that it does, I think that it will, we will see that the diff between those demonstrates that. So that's all. That's the Flux Secretary. He's really cool. We can actually run this outside of the Flux mini cluster, but I'm showing you in this context because it's easiest. So thank you for watching this pajama demo. I'll see you later this week.